What did we discuss last class? Anybody? We continued our discussion on piezoelectric sensors, right? What did we look at? Hello, can you guys hear me?
Yes, sir.
Yeah, okay. See, we looked at the equivalent circuit for piezoelectric sensor. What is the equivalent circuit? Okay, looks like nobody is in the mood to attend the class today. Okay. Um,
Sir, one current source parallel to that one capacitor.
right, okay. Okay. And what is this current source? Now, can you explain why there is a capacitor and why there is a current source? What is the reason? Why is there a capacitor? That's a little easier to answer. You have your piezoelectric crystal. Say we are talking about a transfer. You apply a
To
force.
store the charge. I mean, whatever current you're applying here is basically storing the current itself.
Right, but that's not the reason why it is there though. The reason it is there is because the way we use the piezoelectric crystals are in general dielectrics. When you apply a force, there is some charge separation that is generated, and the way we probe this charge separation is by putting metallic contacts on top and bottom of the piezoelectric sensor, and then by looking at the voltage. Okay. Now, because you have two metallic plates separated by dielectrics, there is in fact you in effect make this into a capacitor. So that's the reason why you have the capacitor here, which represents the two metal plates separated by your piezoelectric sensor. What about this current source? I mean, we could have, see, because we are looking at the voltage, we could have said we are modeling it like this, right? A voltage source in parallel with capacitance. But why do we not do this? And why do we choose this? See, that's because the your piezoelectric sensor generates charge in response to force or stress, and not voltage. So if it was generating voltage in response to stress that is applied, then it would make sense to model it like this, because the voltage that is generated by the sensor is controlled by the force that is applied. What is actually generated is just charge, and voltage is the way of sensing that charge. Okay? And since we don't have a charge generator, we use a current source, and the amplitude of the current that is generated by this current source is in fact not proportional to the force, but proportional to the derivative of the force. Um, because now your piezoelectric crystal generates charge, What is the problem of the sensor now? So if we were to take the piezoelectric crystal, we said it will generate a voltage V, because you have a capacitance C and the charge Q is deposited on the capacitor because of the force that is applied. So there will be a voltage V. That's it. Now we can put this through a voltage amplifier and then get V out, which will be some gain into V. What is the problem with this arrangement? This arrangement is sensitive to stray capacitances. To address that, this problem can be addressed if you use what is called a what kind of a circuit is this? This is your VR.
Charge.
This one. And if you replace the piezoelectric crystal by the equivalent circuit, how does this work then? Why is this not sensitive to the stray capacitance? This is because of your lead wires.
So there is
So
current
the
only in
current
the upper side of the wire. Like there is no current in the lower side of the wire.
Right. So because of the high gain of your op amp and the way you've connected this, this point is at virtual ground. That means the voltage difference across the capacitor itself is zero of the piezoelectric sensor. There is no charge deposited here. So the current is forced to flow through this capacitor and then come back through the op amp to the piezoelectric crystal, charging this. If current is flowing in this direction, charging this. So your P naught will be minus Q by Cf. Okay, and this 1 by Cf is kind of your gain now. This is your output, this is your input, and this is your. And then we looked at one last property of your piezoelectric crystals, right? What is that? If you apply a force like this, zero force, and then some non-zero force, and then it's back to zero force again. What will be the response of what will be, so if you were to plot the charge generated by your piezoelectric crystal in response to this particular force profile, what would it look like?
It will be
Initially, it
decaying.
would
Okay, what will happen here? And this will be the no, sorry. What will happen here?
It will shoot up.
Right?
For
And
that decaying.
then it slowly decay. And here,
It will be shoot down.
like this. So what does your piezoelectric crystal behave like? What kind of system is this? Or what kind of a filter is this?
Maybe a band stop.
Band stop. Why is it a band stop filter?
In between allowing anything.
Sorry, can you repeat that again?
In between, it's not allowing anything, and in the
Hey, hold
initial.
on. Hey, hold on. This is time axis. This time, not frequency.
High pass.
It's behaving like a high pass filter, no? Here, what will happen if I apply it an input like this? Constant force after time t equals some time, right? The response would look like this. So initially the response, let's say it was 0. Go on. So once you let the sensor settle down, right, here, it produces 0 charge for a constant force. Whereas if the force changed by a here there is a large change in the force, there it produces a large output. So this behaves like a high pass filter. So in fact, if you remember, a simple example of high pass filter is this circuit, right? What will happen if you apply a step input to this? Let's assume the initial charge on the capacitor was 0. What will be the output VR if the Vn went from 0 to V0? What will VR look like in this case?
It will be a decay. Gradually increase.
Sorry, can you repeat that again?
It would gradually increase from 0.
Like this, is it?
Yes, sir.
Hey, why would that be?
So because initially the capacitor will be charged. It will.
No, it won't be, right? That's why I said initial charge on the capacitor is 0. So there is no voltage across the capacitor. The moment you switch on the voltage, no? The voltage difference across the capacitor is 0. So all the voltage appears across your resistor. And then the moment a current starts flowing through the capacitor, it will start charging the capacitor. And as the charge on the capacitor increases, there is more and more voltage drop across the capacitor. So the response, in fact, will look like this.
Sir, excuse me, sir. Is it like it will? You said that it will act as a high pass filter. I mean,
Yes.
don't you think it is actually looking like a band pass filter? Because at the rising edge we have some frequency, and as we move forward, it just keeps on decreasing and decreasing, and then it goes to zero,
Yes.
almost.
Yes.
So in that space, uh, I mean, looking at how the high pass filter behaves and how the band pass filter behaves, the plot is very different. So, I mean, I'm not able to get around with the fact that it is acting as a high pass filter, in short.
Here, see, this is basic signals and systems, right? And we also discussed this in one of our earlier modules. So I suggest that you go back and then brush up your fundamentals on high pass filter, band, all these different filters, and I'll propose you this. If you have MATLAB or Simulink, build a band pass filter, okay, high pass filter, and apply a step input and see what the difference is. In fact, build a first order high pass filter. This is the first order high pass filter. You can't have a single order band pass filter. Build a second order band pass filter. That's the lowest order possible. And then look at the responses. Okay. The only thing I'll say is this. Here the frequency is low. Here you have infinite frequency. If this was in fact a band pass filter, the frequency response looks like this.
Yes.
The gain is 0 at infinite frequency, the gain is 0 at 0 frequency. For a band pass filter would not allow this or this. So you cannot have a large jump here because it is passing through this jump. The only filter that will pass through this jump is something that allows all high frequencies. Alright, okay. With that, we'll move on. Otherwise, we'll use a lot of time discussing this. So I suggest you try this to get a better handle, better intuitive understanding of what is going on. we'll move on to flow measurement. Flow and volume, we'll try and cover both of them today. Right. Often when we talk about flow rate, right, what we mean is, but there are two things we could possibly be talking about. One is volume flow rate. Volume flow rate is, let's say you have conduit through which some material is flowing. This is the area of cross section of your tube or your conduit, and then some material is flowing out. Right? Volume flow rate is simply how much volume of material flows through this through a cross sectional area in unit time, and the units of volume flow rate are meter cube per second. Another possible flow rate that people will often talk about is mass flow rate. Is the same thing. You're not looking at the volume of fluid that flows through, but the mass of fluid that flows through in a unit second, in unit time. Okay. If, let's say, there is a fluid that is flowing through this cross sectional area. Let's say let's assume that the average velocity of the fluid across this cross sectional area is v. What is the volume flow rate now? How will you compute the volume flow rate Fv, knowing A and the velocity of the fluid, the mean velocity of the fluid? Let me put it that way.
A into V, sir.
Right. So A into V bar will give me the volume flow rate. Are the units correct? The unit here is meter cube per second. What is the unit of velocity?
Meter square into meter per second.
Yes, sir. Velocity is meter per second. This is meter square. So the units are okay. How do you calculate mass flow rate though? For the same situation? What would you need? Can you we know A, we know V bar. Can we compute mass flow rate from this?
Yes, sir. Rho AV, sir. We need to know the density of the fluid.
Rho into Fv will give me mass flow rate. Okay. And again, in physiology, most of the times we'll be interested in volume flow rate, so that's what we'll primarily focus on. But if you know volume flow rate and you know the density of the fluid, then you can easily calculate the mass flow rate as well. Okay. See, some of the areas where flow is essential is, for example, we are often interested in knowing blood flow rate, which is an important physiological parameter of interest, and we might also be interested in rate at which somebody is inspiring or expiring through their lungs. Okay. So these are two examples of situations where we are interested in knowing flow rate. Okay. See, we'll primarily focus on blood flow. One of the parameters that is of vital importance is the cardiac output. Okay. Cardiac output is simply defined as the amount of blood pumped by the ventricles of the heart. This is again volume flow, and the definition is cardiac output is simply stroke volume multiplied by heart rate. Stroke volume is simply the volume of again, these are average numbers. We're looking at average numbers here. Stroke volume is the total volume of blood that is pumped out by the heart during each contraction. Okay. What would be the unit of this unit of stroke volume? It will be meter cube, because it's simply the volume of blood pumped every heart rate. Every heartbeat. And HR is the heart rate, which is simply number of heartbeats per second, which is basically 1 by second. The unit of this. Cardiac output is important because it tells us something about the ventricular function of the heart. So this is of vital importance in cardiology. There are several methods to do this. We'll look at some of the methods. These are all methods that were proposed long time back, but they are still useful, and some of them are gold standard methods. Okay. We'll first look at the fix method. Before going into this method, right? Let's try and understand the principle behind the method. Again, as I said, this is originally proposed a long time back, 1870, by Adolf Fick, and this is also a fairly accurate and method that is also considered a gold standard. Okay. Okay. Let's assume that you have. I mean, I've drawn. Let's say you have the lungs. Right? Blood is being pumped into the lungs by the heart. Okay. What the pulmonary arteries take blood into the lungs, and then the pulmonary veins take it out. Okay. And what happens in the heart? Sorry, not the heart. What happens in the lungs?
Gaseous exchange.
Sorry, can you repeat that again?
Gaseous exchange will happen.
Right. So there is exchange of gases that happens at the lungs. Okay. So Fick's idea was is like this. Okay? Let's assume there is a constant flow of blood through the lungs. Okay. There is some constant flow rate that is established, average constant flow rate that's established in the lungs. Okay. And there is some exchange of material happening here. Okay. If there is some exchange of material happening here, the blood is gaining oxygen or losing carbon dioxide. Then, if we monitor the concentration of, let's say, oxygen at the input side, and we monitor the concentration of oxygen at the output side, we should find that CO is greater than Ci, because oxygen is diffusing into the blood in the lungs. Okay, and where is that oxygen coming from into the lungs?
From the atmosphere.
Right, from the atmosphere through your nose. Right. So now, in addition to monitoring Ci and CO, if you also monitor the rate at which oxygen is being absorbed into the lungs, so this can be done by looking at the concentration of of oxygen in the air that goes in, and the concentration of the air that comes out, and the difference would tell you how much oxygen is absorbed in the lungs by the blood. Right. So that is this dm by dt, the rate at which this is mass flow, rate at which or the grams of oxygen that are uh, absorbed in the lungs per unit time. Okay. Now the question is, if we have these three, can we say something about this flow? Okay. It turns out there is a way, and that is the method that Fick proposed. Fick simply said, if by monitoring the concentration of oxygen in the input side and the output side, and looking at rate at which oxygen is being being absorbed in the lungs, we should be able to compute or determine the flow of blood through the lungs, the volume flow rate. Simply this. Okay. Does that make sense? The ratio of rate at which oxygen is absorbed in the lungs divided by the difference in concentration between the output and the input will simply tell you the flow rate. Why is that? How do you get this? Can you explain why this might be the case?
Yes, sir. So we can explain better it with example.
Uh-huh.
If 250 grams
Hello?
put and
Yeah.
200 grams of oxygen. Hello, sir. Am I audible?
Yes, yeah, I can hear you now.
So we can explain this with an example actually. If
Sure.
200 grams of oxygen is there in the blood in the input and 250 grams of oxygen 200 ml actually.
Right.
250 ml of oxygen is in the output, and let's say uh, some amount of 200 ml of oxygen is coming from the outside. Then, like how much is absorbed in the 1 minute, we can calculate from here.
Sure. Okay. See, also, if you look at this, right, this says your CO is proportional to rate at which oxygen is absorbed. Does that make sense? Would the rate at which I absorb oxygen increase as my flow rate increases?
Yes, sir.
Why is
The
that?
flow rate, uh, flow rate basically.
No, sorry. Can you please speak to your closer to your mic, please?
So, am I audible?
Yeah.
Yeah. So, the flow rate is like the amount of the concentration of the oxygen that is being absorbed by the body, by the lungs. So, and depending on that, how much of it is getting delivered to the tissues is also kind of dependent on the mass flow rate of the oxygen concentration in the body. So, in that way, cardiac output will be proportional to amount of the oxygen consumption. Sorry.
Okay. All right. See, again, yeah, something similar to what she said. More flow there is, that means the moment, let's say, the blood gets oxygenated in the lungs, it gets pushed out. If the flow rate is high, that means there is more and more blood available with low oxygen concentration, which can absorb the oxygen that is coming in. So your uh, rate at which oxygen is absorbed will go up if the blood is flowing at a relatively fast uh, pace. Okay, and it says it's inversely proportional to. Does that make sense?
Yes, the concentration gradient should be inversely proportional, right?
Why is that? So here, this
So
means if the concentration does not change, right? What does it say about my cardiac output?
concentration is not changing. The cardiac output is zero, so then
No. Cardiac output is
So diffusion is impaired.
yes. So it's flowing so fast that nothing. There is no time for diffusion. Okay,
okay.
that's the idea. And here, the units of dm by dt is say grams per second. In concentration here is gram per volume. So what you will get volume per second. That's the basic idea. Okay, now let's do a simple example. This is the rate at which this is the concentration of oxygen in inspired uh, gas. This is the concentration of oxygen in the expired gas. This is measured over, this is average concentration measured over 3 minutes. The total volume of uh, gas that was exchanged was 26 ml, again over a period of 3 minutes. And the average arterial oxygen concentration was 195 this year, and it was it was 195 here, 132 here. I should have changed that one. I should have changed this because this is pulmonary vein, this is pulmonary artery, but you get the point. The question is, what is the cardiac output now? It's the denominator is simple, right? It's simply 195 minus 32. This is ml per liter. What about the numerator? How will you compute the numerator?
Is it 6.87?
I don't know the number, but what is the
Okay,
numerator?
so 50 into 26 divided by 3. So
Why is that?
210 minus 160
Right.
into 26 liter of blood
Sure.
in
That
3
is the
minutes.
total ml of oxygen or consumed over 3 minutes. So the average consumption of oxygen is 50 into 26 divided by 3. I don't know what this number, and what is the unit here? Will be ml per minute. Whatever you get here will be liter per minute. What does it come out to?
I guess
6 point something, is it?
6.87.
Right. So that's the cardiac output in this particular example. So that's one of the methods. Another method. So here we are looking at here the property that is used here is if there is fluid flowing through a compartment where some exchange of material is happening, then by looking at the rate at which material is getting absorbed in this compartment, and by monitoring the concentration of this material at the inlet and the outlet, we should be able to compute the average flow rate. That is the principle here. The next two methods that we look at are slightly different. Here the idea is, if you have, let's say, a tube through which some fluid is flowing, okay, and you insert a syringe here, and then you pump in some external material, okay, let's say some dye, okay, and you have a detector here that's placed downstream that can detect the concentration of this dye as it flows past the detector. Okay, let's assume a simple scenario where let's say dye is introduced, and the dye gets introduced in such a way that it's flowing in a nicely packed volume like this, and it's mixed with the blood. So blood is, let's say, flowing at a velocity v. Okay, and let's assume that this is mixed and this whole thing is moving with the velocity v now. Okay, let's assume the area of cross section is A, and let's plot what the detector would see. What will the detector see now? Initially, there is no dye, so it will see zero concentration. And then, as this mixture of your blood and dye passes through the detector, you should see something like this. Right? So, there is the region of the fluid which is now well mixed with the dye, and as it passes through the detector, this is the concentration. This is the concentration profile that we would see. So, this is C, this is dye. Let's say it's got some like C now. Now the question is, can we use this to find out flow rate, FV? If so, how would we do that? Okay, let's do a thought experiment, right? Let's assume that the flow rate was very slow. Okay, what would the concentration profile look like as detected by the detector? Fine. Say we are looking at slow or very low flow rate. And let's say this is moving, this bolus is moving at this particular rate. What will happen? What will the concentration profile look like from the detector?
It will gradually increase and gradually decrease with the slope.
Hey, no, sorry. Here, initially the assumption I asked you to make was, let's say there was a clear boundary here. The way the bolus was put in such a way, and let's assume the detector is fairly close to where the dye was introduced, so that this bolus is not mixed along with the blood along the length of the tube.
Okay.
Similar as the first one, sir.
Right, but what will change? The height will be similar because the concentration is the same.
Yes, the time will be greater
Right.
time.
So if it is moving at a slow rate, right, then you would see something like this. Whereas if it is moving at a very fast pace, you see something like this. Right. Now, can this be used as a clue for finding out the flow rate? And
Yes,
let's
sir.
assume that we know the mass of the dye that was introduced. That we know because we introduced the dye.
Yes, sir. We should know the volume then.
Sure. How will you find out the volume?
The mass by rho.
Mass of a rho of what? No,
Uh,
see, mass is the mass of the dye that was introduced. Okay, that dye is now mixed and is now uniformly mixed in a small volume of blood. Let's say the length of this bolus is L and the cross section is A, right? And the volume of this region would be simply, right?
yes, sir. Somehow we have to get L value.
How will we get? How is L? So how is L related to, let's say, uh, V, the velocity of the fluid?
Yes, sir. We know the time. We know the length. Like the
Right.
length is
So
covered with the
this we know,
time.
delta T. So instead of this, instead of using two V's, let me call the velocity phi. We'll call it phi. Okay. This is the velocity of the fluid. That means here it will simply be delta T is the width of this pulse. Because if this is moving at a velocity phi, this bolus will take delta T seconds to pass through the detector. Now, this is unknown, this is known, and this also we might not know A because we might not have any direct measurements of the cross section of the tube into which this is inserted, and volume also we don't know. But can concentration tell us something about the volume? Or can we get the volume from the concentration? Okay. See, this mass that was introduced is assumed that it's well mixed in this region, right? And the volume of this region is phi. That means what is the concentration of this material in this volume, of the dye in this volume? Let's say
Mass
it's
upon volume.
Mass of the dye by volume.
right.
Mass
Total
upon
If we
mass.
know the
volume.
mass that was introduced, we can measure the concentration from the detector. That means B is simply M by C, right? So we replace this here. M into C is delta T. This is FV, volume flow rate. So our volume flow rate is simply, sorry, M by C. Is that clear? So if you have a scenario like this and we are able to measure the concentration through a sensor, and if this assumption is in fact correct, then we can find the flow rate, volume flow rate, by simply knowing how much dye was introduced, by measuring the concentration of the dye in the blood as it passes through the detector, and the duration for which, and the width of the pulse. Now, if delta T is small, as in this case, you see FV is higher. If the concentration is low, sorry, here, see the concentration will depend on both the mass that is introduced and C, and the combination of this will tell you something about the volume that is flowing past. So M by C, so the volume flow rate is in fact proportional to M by C. If M by C increases, then your flow rate is higher for the same delta T. Okay, all right. Now, if that is clear, this is a simplistic scenario, right? A very simple scenario where we've assumed that the dye that's mixed with the blood flows retains a shape like this, or that the detector is fairly close to the point at which it is introduced. But what will happen in general is this. Introduce the die here. The flow of fluid through the tube will have a profile like this. Right? The velocity of the fluid is maximum at the center, and then it goes to zero as you get closer to the walls. Okay? So if you introduce a die here, what will eventually happen is the die, as it travels through this tube, will eventually take a shape like this, like a teardrop. And now, if you have a detector here, what will the shape of the detector's output look like? Let's say the leading front of the teardrop reaches this point at this time, t0. So initially it will be 0.
It suddenly increases and gradually decreases.
Okay, so you don't have a situation like this, but you have a situation like this. Okay, and because we are only interested in average flow rate, the way now this situation is dealt with is, instead of saying flow rate is m by c delta t, this is simply the area under the curve. Yes. You do the same thing here. And how will you find the area under the curve? Let's say this is C of t. So we know m that was introduced. We know C of t. Is that clear?
So I didn't get the last part, wherein the third situation.
What is which situation?
The third situation where this, this one.
What is not clear?
So how, I mean, the situation is not clear. I mean, you basically, the ma- the flow of the dye along with the blood would be, it would turn it into this shape.
It's not clear why it will happen, is it?
No, I mean, I missed this part. Could you please once again explain this one?
Okay. I don't know what you want me to explain, but again, I'll maybe repeat what I said. Okay. See, if within let's say a blood vessel, right, or any tube where there is some fluid that's flowing, if you look at the velocity of uh, fluid, let's say you take a cross section and you ask what is the velocity of fluid at any point on this cross section. Okay. If you look at the velocity, it will usually be like this. The velocity of the fluid will be maximum at the center, and it will go to zero as you go to the edges. Okay? So now, if you introduce the die, whatever part of, let's say, the die was introduced like this, right? The part of die that is close to the center of the tube will move at a faster velocity, whereas these guys will have a lower velocity. Now, as this moves out, there is more concentration of dye here and more concentration of dye close to the walls of your tube, so they will start diffusing in. So over time, your dye will take a rough shape like this. See, of course, there won't be a clear boundary like this. The boundary will be hazy, but in general, it'll take a shape like this. And if when it passes through the detector, the shape of the curve that we will typically see will be like this.
Area under the curve.
No, this is
Yes,
the
sir.
shape of the curve. If you look at the previous example, the previous scenario, we said flow rate is mass divided by C into delta T, where C was the height of the curve, delta T was the width of the curve. That's because we had a rectangular pulse. But here we don't have a rectangular pulse. Okay. One way of interpreting this C into delta T is that it is the area under the curve. So we can say mass flow rate is simply volume flow rate is simply the mass of the material that was introduced divided by the area under the concentration curve. So
Yes, sir.
we can replace C into delta T by this integral.
Yes,
Or
sir.
see, another way to interpret this is you're simply multiplying integral E naught d1 E of t dt is simply the average value of concentration bar multiplied by d1 minus t naught, which is delta t. So if we place this curve by a pulse by the mean concentration and the width of the pulse, t naught to t, and that
Yes,
will
sir.
give you. So this is another way of finding out volume flow rate.
Yes, sir. Thank you, sir.
Okay, all right. Okay. See, there are a few things that now we have to be careful about this method. Of course, the dye. If you're introducing a dye like this into the blood, you of course have to make sure that it is not something that is toxic, that does not badly react with the tissue or the blood. And we also have to make sure that it is not something that is very quickly cleared by the blood. For example, if you introduce it here and by the time it reaches here, if part of this dye is now catabolized and then converted into something, then of course your estimates would be wrong because you've assumed that this mass Mi is still present in your circulatory system, which is being picked up by your sensor. So those issues have to be kept in mind. And there is another problem as well. Like I said, the concentration curve would look like this, but because and this flow is not linear, but in fact it is the dye, if it is, let's say, not catabolized by in the body at all. That means once you introduce it here, it is going to eventually stay in the blood forever. Okay, that means if you a typical curve might not look like this. In fact, it might look something like this. Goes up and comes down. It does not go to zero, but some blood might stay around. And now, if you take the area under this, right, it does not die down at all. If you take the area under this, it it can go up to infinity. So you can underestimate your cardiac output. So what people often do is when they see a curve like this, they usually detect this point and then assume an exponential decay and then use this for the integral. This is because of recirculation of the dye within your circulatory system. Okay, so these are all some additional details that you have to keep in mind with this indicator dilution method. Okay, is it clear? So see, one way this might be used is like this. So if you have, let's say you have your heart, you have your blood flow to your right atrium, and then you have your valve, the right ventricle, then that goes into your pulmonary circulation. What people might do is you take a catheter, you insert the catheter and then put the detector here. This is your detector, and you might have another port here which puts out the dye. So you insert the dye here, and then it gets mixed here, and then it's pumped through the detector, and then you detect your concentration from here. This is one way in which it is done. To measure cardiac output. See another method. See here we were relying on the concentration of a particular dye. We can do something similar, but this time instead of looking at the concentration of a particular material, we can kind of look at the concentration of heat. Okay. Again, the idea is again very similar. You have a chamber through which your fluid is flowing at some rate f, and let's say the temperature. Let's say I mean you're talking about blood, right? Let's say the temperature of blood was TB, is TB, the average temperature of the blood. One option is instead of introducing a dye, you introduce a bolus of cold saline, okay, whose temperature is Ti and Ti is definitely less than TB. Okay. Now, let's say we don't introduce anything here. Let's say the temperature of blood is TB, and you've got a temperature sensor here, and you're looking at, instead of C of T, let's say it's TB of T. So if you now look at the output of the sensor versus time, it'll hover around TB. Right? Now, let's say you introduce a bolus of cold saline at temperature Ti, which is lower than TB. What will happen to the curve TB? Will it keep continuing like this? What would the shape of the curve look like for TB versus time at this point? Basically, temperature of the blood that is passing through the through your temperature sensor.
So will decrease slowly and then become hot.
So what will happen is it will decrease and then go back to this. Okay. See, one advantage of this method is if the bolus is small, right? There is no problem with recirculation because by the time the blood gets your cold saline gets mixed with the blood, the temperature will go back up to TB. So there is no problem of recirculation that you had with your dye. And again, by simply looking at the area under this curve, we should be able to say something about the flow rate. Last time we had m divided by integral C of t dt. This is similar to that, except now mass would simply become the heat that was introduced divided by in heat introduced per volume into time, okay, which is then
So
used
what?
for computing.
So what is Ti here and
Yes, I'll clarify this. Okay.
yes,
Ti is the temperature of your indicator, your cold saline. And let's assume this is time t equals 0. TB of 0 is basically temperature of the blood at time t equals 0. Basically, it's the baseline blood temperature. Vi is the volume of the indicator. Rho I is density. I means indicator, so I'll leave that out. And Ci is its specific heat. So this is all for the indicator. And whenever you see B in the substrate, that is for the blood. Okay. So your flow rate is, again, as I said before, it's computed similar to this, where it's total heat that was gained by your indicator divided by the heat per unit volume multiplied by your time. So that will give you. Okay. So this is also another method which is commonly used, in fact, more than the indicator dilution method discussed earlier. The idea is again similar. So instead of introducing the dye here, you introduce cold saline or some other fluid, which is then picked up by a temperature sensor here. So the D here is now a temperature sensor. Okay, so that's another way of computing cardiac output or measuring cardiac output.
So here we are assuming the area of the artery to be constant, or area of the artery doesn't matter at all, as we are considering concentration.
Sorry, there is no concentration. This is specifically. Sorry.
No, in the previous case also, sir. I'm telling if the area of the artery is changing, then does
Yeah,
this
that would
hold
not
true?
matter. See, that is already obtained from your concentration. No? The
Okay,
concentration
okay.
is amount per volume. So the cross section of the artery and the flow rate is taken into account is provided by your concentration.
Yes, sir.
Okay. Now, so that's measuring cardiac output. Let's say now we are interested in measuring the flow in some blood vessel. Okay. So again, if you looked at the measure of the iota, then that could be a measure of your cardiac output as well. Okay. We know that blood is a conducting fluid. Right? So one way to measure velocity or velocity of the fluid is by applying a magnetic field perpendicular to the flow of your conducting fluid, and by monitoring the voltage across voltage that is developed across the vessel, because you have positive and negative ions that are flowing through this blood vessel. So if you apply a magnetic field, these would get separated uh, in different directions, which would result in positive ions flowing in the top portion of your blood vessel and negative ions flowing in the bottom portion. That means there is charge separation. That means there is an electric field. That means there is an electric potential that is set up. Now, if you place two electrodes on the top and bottom of this vessel and you measure the voltage, you would see a voltage that is proportional to the magnetic field that's applied and the velocity of the fluid that is flowing in. And if you now know the area of cross section, you should be able to now calculate volume flow rate. Okay, that's the principle here of the electromagnetic flow meter. This again is used, but note that this is also invasive. So you have to cut open, expose the blood vessel of interest, and then apply the magnetic field and measure the potential on the surface of the blood vessel. I mean, I basically explained the same thing here. If you've got positive and negative ions flowing in this direction, then you would end up having positive ions being pushed to the top, negative ions being pushed to the bottom. That means there is an electric field that is set up, and that we should be able to measure as a voltage difference, or E. Now this V will be proportional to your U and your magnetic field. Okay, so notice that what you will measure here will be the average velocity, because again, if this is a blood vessel, the blood flow, the velocity profile of is likely to be like this. So what you will measure here will be the average velocity of the contents of the tube. Okay. This is another method, and all of these are in some way invasive. The electromagnetic flow meter is of course highly invasive because you have to expose. The other ones you can go through a catheter, so it's I guess slightly less invasive. Uh, there are non-invasive ways of doing this as well. Okay, that is using ultrasound and using the principle of using the Doppler effect. Okay, uh, what is the Doppler effect? What do you remember?
So when the sound source is approaching a receiver, the intensity gradually increases.
Sorry, is it the intensity? Intensity will of course increase, right? But Doppler effect
Yes.
is not about the intensity, no? What is it about?
Frequency, sir. Apparent frequency.
Right. So what will happen? So for example, let's say you have a source and a detector. The source is transmitting uh, some uh, some waves with some frequency f naught and some velocity c. Okay. Let's say the source and receiver are stationary, then the receiver would receive the signals that are coming from the source. And if we were to ask the receiver what is the frequency of the signal that's coming in, the receiver would say the frequency is f naught. No problem. If they are not, if they don't have any relative motion with respect to each other. Okay. But if one of them is moving, either the source is moving towards the receiver, or the receiver is moving towards the source, or the other way around. Okay. Then it turns out that the frequency that is reported by your receiver will not be f naught anymore. Okay. The frequency reported will be f naught plus delta f. There will be some change in the frequency that is perceived, and that change in frequency delta f is related to the speed of the waves, the original speed of the wave, which is c. It is related to the original frequency and the velocity of the relative velocity between the source and the receiver. Okay, so change in frequency will be v by c into f naught. Okay, when both of them are not moving, when v is 0, there is no problem. Delta f is 0, so the reported frequency will be f naught. But if the velocity is positive, if there is a non-zero velocity, then you will report a change in frequency. Okay. Now this is when your so here I think this should have been, so if moving away is positive velocity, right? If you move closer where velocity is negative, then you'd report higher frequencies. If they're moving closer to each other, then you'd report higher frequencies. If they're moving away from each other, then you would report lower frequencies. So that's it. F minus delta f. Okay. So this is if both of them are moving along the line joining the source and the receiver. But if the movement is in some other direction, let's say the velocity is not pointed along this line, but some other direction, okay, then what matters is the component of the velocity that is along uh, this line. Simply v cos theta into f naught by c. Okay, that means if you have a source and your receiver, this is your source, is moving in a direction orthogonal to the direction of the incoming wave. Okay, so this is the direction in which the wave is coming in. If the receiver moves along the direction in which the wave is traveling, then this applies. If it's moving at a slightly different direction, then you apply this. You'll have to account for the difference in direction by cos theta term. That means if you move in such a way that you're always moving orthogonal to the direction of the wave, then delta f is 0. That means you don't have any change in your apparent frequency. You will report f naught. That's because if you're moving orthogonal to the direction in which your uh, wave is traveling, then your distance with respect to the source remains the same. That's why there is no change. But in any other, if you move in any other direction, then there is a relative change in the distance between the source and the receiver that's taking place over time, and that will always lead to a change in the frequency. And this is the principle that is used for Doppler ultrasound. Yeah, is it clear? Okay, I'm assuming that's it's not too complicated. Okay, all right. Right now, okay, this is how this is the principle at least. Okay, you have a blood vessel that's say inside the body. You take an ultrasound source, okay, and you transmit some ultrasound waves. And because your blood is not some uniform liquid, but it's got lots of different particles, especially red blood cells, right? So basically some particles inside. So if ultrasound impinges on these particles, they're going to reflect some of it back. Okay, and it's this reflection that we pick up, and the difference between the transmitted frequency and the received frequency will tell you something about the velocity of the RBCs, and so the velocity of the blood. So that's the idea. Okay, but there is a slight difference here. Okay, in the previous case, you had the source, you had the receiver. The source was transmitting, and the receiver was receiving, and we said there was a relative motion between the source and the receiver, and the relative velocity was termed as v. Okay. But here there is a slight difference. So the ultrasound probe that you have on the outside has two components. Has both the source and the receiver. Okay, and uh, what is being reflected, I mean, what is being received by the receiver is sound that is, or ultrasound that is reflected from the RBCs, and what is being received by your RBCs are the ultrasounds that are generated by the source. Okay, so in the previous case where delta F was V by C into F naught, in the current case there will be an additional factor of 2. That's because your source transmits, and the intermediate receiver, which is your RBC, is moving with some velocity v. Right? So there is a change. So the frequency that is perceived by the RBC will be basically this v by c into f naught. But then your RBC is reflecting that wave back, so it's acting as a temporary source, and the source is moving with the same velocity. So whatever is reflected back will undergo another frequency shift because now the source is moving. So that is what contributes to this factor 2. So there will be a factor of 2 because now what you are sending and receiving is being reflected by an object that is now moving away. This will be the same, for example, if you had the, I mean, it's like you have the source and the receiver here, both are stationary, but sorry, but this is moving with the velocity. Here, if this is f naught, what will be received here will be f naught minus 2v by c. Okay. Or another way to think about this is if you have a reflecting surface like this, right? It is equivalent to the source and the receiver like this, but the receiver is moving at velocity 2v. Okay, that's why you have the two. So now this should tell us something about. With this, we should be able to. We can find this. We know the velocity of the ultrasound that is sent in. We know f naught, and let's say there was a way for us to figure out theta as well. Then we should be able to find the velocity of your velocity of blood flow. Okay, that's the idea. And if you know the area of cross section, then you should be able to get volume flow rate as well. See, the way you do this, there are several ways of in which the data that is received back is processed to obtain your velocity, and often you what you'll obtain. Okay, let me quickly go through the process. I'll not get into the details of how this might be done, but the idea is this. Okay, you're transmitting a signal x of t, and then you're receiving y of t. You know the frequency that you sent in, okay, and what is reflected back. Now, let's say these RBCs are all moving at a constant velocity v. Okay, now if you look at v of t and you take its Fourier transform, right? That means you look at its frequency count. If you look at the input signal, right, f, this is your, let's say this is power in your input signal. This is for your input x of t. The input signal will have some power at f naught. Okay. Now this is sent out to your to the blood vessel, and then what you get is y of t. And if you take the Fourier transform of this, let's say the blood is flowing at a velocity v, and the angle is theta. Now, if you take the Fourier transform of y of t, what will the plot of Fourier transform of y of t look like now?
So if there is noise, then it will be like it will be a spike at f minus delta f,
Right.
or there
So
will be
let's
smaller.
assume there is some noise. Right? So you might see something like this, and let's say this is f naught, and let's say f naught delta f was negative, right? So that means you might see something like this. And if you look at the peak velocity, this will be f dash, and f dash minus f naught will give you your, or the other way around, minus this. Okay, and this will tell you now something about the velocity. Okay, but here this is an ideal scenario where all of them were moving at the same velocity, but all of them might not be moving at the same velocity. Some RBCs might be moving slower, whereas some of them are moving faster, but all of them might still be moving in this direction. Okay? In that case, what would your the Fourier transform of your received signal look like now? Let's say this is f naught, so there's still some noise.
There would be several frequency at
Right.
above f.
Right. So you might see something like this. Okay. So, in fact, let's say there is a spectrum of RBCs are not just moving at some specific velocity v1, v2 to vn. Let's say there is a spectrum of possible velocities, because there are lots of RBCs. Then we can assume that there is a continuous distribution of velocities that they have. So you might see something like this. And if you now take the average, or if you take this, right? This region of the curve, this will tell you, and let's say you take the average frequency of this curve, then that will tell you something about the average velocity of your RBCs. But if you look at the details of the curve itself, that might tell you the amount, the percentage of RBCs that are moving at a particular velocity. Okay. Right, so that's the idea. Okay, what will happen if you received signal is like this? What does that tell you?
The uniform flow of all the RBCs.
No, here.
Doppler effect, change of frequency will be 0.
The received pulse also has a peak, but a smaller peak, of course, compared to the original signal at f naught. What does it tell me?
Okay. There is no delta f, so V is 0.
Right. So that means the blood is not flowing. It's stagnant. Okay. What if you see something like this? These two are more or less of amplitude A, and this is A by 2. This is f naught. This is f1, f2, f3. And see, this is the noise floor, right? This is noise. So anything above that is what you will consider as meaningful.
Flow
What might that tell me about the distribution of velocities in my blood flow?
Most of the RBCs are flowing at f1 frequency.
No, see here, f1 will correspond to some velocity v1, f2 will correspond to some velocity v2, v3. Because the peak is higher, that means there are more RBCs reflecting waves back at this frequency. That means, and these two more or less have the same amplitude. That means you can say equal percentage of RBCs are moving at velocity v1 and v2, and maybe like half of them are moving at velocity v3. So I'm giving you a rough idea about how this is used. You might not be able to exactly say what that this is definitely half the number of RBCs are moving at v3 compared to v1 and v2 or something like that. But this is the general principle, at least. The size of the intensity of the frequency peaks tell you about the number of RBCs that are reflecting the ultrasound back at that particular frequency. Yeah. Okay. So that's the ultrasound method. So that's the ultrasound method where you're looking at the Doppler shift. There is another way to do this as well. There, here, this is your limb, and that is the blood vessel. Then you had the source and the detector here, source detector, and this is transmitting, and this is receiving, and things are moving like this. Another method is called the transit time method. Again, here the idea is simple, but here you'll have to expose the vessel, so you have your body, and then you expose the vessel that is underneath. Then you place a source here and a detector here, or a source and a detector here and a reflector here, either way. Let's say this is the source, the detector. Now, let's say the blood is not moving, right? Blood is stagnant. If you transmit, let's say, a signal from here, let's say you're transmitting a pulse, right? The pulse is transmitted at some time here. What will you see at the detector? Let's say the detector does not detect anything. After some time, you'll receive that pulse, right? Let's say the pulse looks like this. What will this delta t depend on? Well, let's assume this angle is theta and that this distance is.
T cos theta, sir. T cos theta and
Sorry, this is t, this is c. No, here, if nothing is moving here, right? If this is d and the speed of your ultrasound is c, then delta t is simply d by c, right? But what will happen now if blood is flowing through this? See, what will happen is that the waves that impinge on your blood will be carried, additional velocity will be imparted on them by the flow of the blood. If blood is flowing in this direction, the waves will arrive faster at D. If blood is flowing in the other direction, if this is the source and this is the detector, then it will be slowed down. And the amount by which it will be become faster or slower is given by, it depends on this angle theta and the direction in which the ultrasound is impinging on your, or being impinged on your blood vessel. This is another way of computing your blood flow by looking at transit times. I mean, you can either use this as the source or this as the source. It depends. It doesn't matter. Okay. All right. So these are methods that are commonly used for looking at blood flow. Okay. Now let's look at a method that is used for looking at airflow. I mean, the idea is again simple here. If you have a tube through which some fluid is flowing, let's say you introduce some resistive element, and this is, when I say resistive, this is resistance to airflow, not a resistance to current. resists fluid flow or airflow in this case. Okay. If that is the case, when you introduce a resistive element here, and if you monitor the pressure of the wave of the fluid on either side of your resistive element, there will be a drop. And if you know the resistance offered by this resistive element and you know the pressure drop, then your flow is proportional to drop in pressure. In fact, similar to your Ohm's law. This is it's kind of Ohm's law for airflow. Where pressure plays the role of voltage, airflow is current, and this R is the resistance to airflow. Basically, resistance to current flow in the case of electrical circuits. Okay, there are. I mean, of course, airflow or fluid flow is a lot more complicated than current flow because you can have laminar flow, and if velocity increases, and if there are sharp obstacles, then you can have turbulent flow where the analysis becomes fairly complicated. Right? If we can assume that the velocity is that the airflow is laminar, then there is a nice linear relationship between your velocity or your airflow rate and your fluid flow rate and your drop in pressure, which is related to the basically the length of the resistive element, the diameter. Can't remember it. So this laminar flow happens. See, there are different ways in which you can introduce resistances here. One way of introducing it is you take piece of material and then you make tiny capillaries throughout. Where here M is basically your the number of capillaries. I forget what mu is. Yeah, let me get back to you with that. I can't remember what mu was. Okay. When you have something like this, then a laminar flow assumption is a reasonable assumption, and your pressure drop is related linearly to your airflow velocity. Okay, and these capillaries, if you look at the capillaries itself, they have smooth orifices like this. Then this assumption of laminar flow is more and more correct. But if they have rectangular orifices like this, then you can have turbulent flow. Then the relationship between your pressure drop and your airflow velocity becomes more complicated. Okay, it's not linear anymore because it depends on kind of u square, and because it change, for example, if u was flowing in this direction, pressure here would be higher than here, but if it is flowing in this direction, this would be higher than this. That means delta p has a sign. So to account for the sign, instead of writing u square where you lose the sign, you write u square like this, where u still contains the sign, and here you have the magnitude of u. So if you plot u square, it will look like this. This is u square. But if you plot u multiplied by u, you basically flip this, mirror this about the negative x-axis. Okay, then you have a relationship like this. Okay, so in general, a reasonable model for any resistive element that we introduce like this would be to consider both laminar contribution from laminar and turbulent flow, and then when you do the calibration, you basically estimate your R and K. Okay, and then use that as a instrument for measuring fluid flow. Okay. Right. Okay. We'll stop here. That's pretty much all of flow measurement that I wanted to talk about. There is maybe one more method which looks at plethysmography, which we will do next week. Okay. Are there any questions so far for today's class?
Sir?
Yeah.
So I have a question. In the this slide of ultrasound. Before that, no, ultrasound below, Doppler flow sensing. In the Doppler flow sensing, you said that the amplitude shows, it basically depicts the mass of the RBCs.
Not the mass. I'm saying number of RBCs that are reflecting at that frequency.
Okay, I mean the amplitude is basically dependent upon the number of the RBCs that are be reflecting.
Yes, here. Imagine like this, right? Okay, there is one RBC and there is
Mm-hmm.
another RBC. Say this is moving at velocity v1, this is moving
Mm-hmm.
at velocity v1, this is at v2. You have your source, you have your detector. You send in
Mm-hmm.
ultrasound at frequency f0.
Mm-hmm.
This one will reflect back at frequency f1. This one will reflect at f2. Okay, let's assume the relative distance of these two with respect to the detector itself is approximately the same. That means the amount of or the intensity of the sound that is reflected back by each of these two RBCs would be more or less the same. So the frequency peak that you see at f1 and f2 would have more or less the same height. Now imagine there were two RBCs that were moving at v2. Okay? There'll be two signals at frequency f1 of more or less the same amplitude, so there'll be twice the intensity.
Twice in.
So you might have something like this. That's what I meant when I say the height can tell you about how many RBCs are moving at that particular velocity, or roughly, or the proportion of RBCs that are moving at that particular velocity.
Yeah. Oh, okay, sir. Thank you, sir.
So this is f1. Okay, all right. If there are no other questions, then we'll